Okay, so this is Chapter 5 from CSE 262, Technology, Ethics in a Global Society. And this chapter is going to review trust, safety, and reliability. So there are three main objectives in this chapter, and they are: why does software fail? Basically, the short answer is people. It is possible making mistakes with the software or people testing the software or hardware for that matter. It's all basically down to people. And people do malicious things with software or hardware, but usually when there's a failure in software or hardware, it is always about people. What are the consequences of software failure? Sometimes minor inconveniences, sometimes injuries, and sometimes death. And how can we help prevent software failures from occurring in the future? Preventing software failures. How? As software gets more complex, preventing failures becomes even more difficult. So there are a variety of reasons of why software fails. Hardware errors or malfunctions, software errors or bugs, programs developed to solve the wrong problem, so programmers get requirements from clients, they develop what they think the client wants, turns out it isn't what, he didn't capture the requirements correctly, so the system was developed to not solve the problem that was originally trying to be solved. Misuse, communication failures, and just plain malice. So let's talk a little bit here about some of the differences between hardware and software. Hardware is a physical computer itself, or laptop, or any device. It has a CPU, a hard drive, input devices, such as mouse, keyboard, monitor, touchscreen, etc. Software is essentially instructions designed to be executed by the hardware. So, for example, a word processing or operating system, or even Google Maps. So, suppose you use an ATM and ask for $100 but only get $80, even though your account was charged for $100. Is this a hardware error or a software error? I'd like for you to think about that, and let's discuss it in our online session. As mentioned above, software errors are referred to as bugs, and at any time a programmer makes a mistake, this is considered a bug in the code. Debugging a program means finding and fixing those types of mistakes. The word bug actually, in this case was literal. The first computer bug was literally a bug that was found in a computer, and that bug was found to cause an issue with the program because it couldn't read the program because of the bug. So that's where the bug came from. So you can read about it here at this link if you want to humor yourself a bit. It's actually a funny little story. So Distra said that we should use the word mistake rather than bug because it emphasizes that humans are at fault. Software error can fail because there is a logic error in the program, but it can also fail for other human reasons. In other words, the software works fine, but the humans misunderstand how to use it correctly. That's a possibility. So as an example that is talked about in your textbook, there was a problem when interpreting a readout as liters when it should have been interpreted as gallons. I think this had to do with an airplane, if I recall correctly. And it caused a lot of problems. So whose fault is that? The goal here is not to point the finger as much as it is to how to prevent it from happening again in the future. Certainly the programmer could do things to make it very clear what the measurement is in this case, so that there wouldn't have been an actual ability to make that human error. So another human error could be due to the programmer not understanding the correct problem it was supposed to be solving. And I was just talking about that, getting the requirements wrong. Malice is people who create software that is intended to do harm. So you're probably pretty familiar with this nowadays. These would be things like viruses, spyware, Trojan horses, and distributed denial of service, or DDoS attacks. Suppose a word processor marks a word as being a spelling error, but the word is actually correct. What kind of error is this? It's probably not hardware. Software, but maybe not a bug. Maybe it's an outdated dictionary, or maybe it's a new word. So there are many languages used today to write code. Java, C++ are some very popular ones today. Ada is actually an older program that still has some life left in it, so it's worth mentioning here. I also believe it comes up later in our discussions. But in general, programming languages all have limitations. Sometimes there are mistakes in developing the programming language itself. So keep in mind that humans make these programming languages, which offers plenty of room for errors. Speaking of limitations, Java is a good example to discuss in this case because, and again, this happens in many languages, but we'll just talk about Java. So Java is really good at adding numbers, and while I could hop out and show you how to do this class isn't based on programming, so I'm just going to talk you through it. But in Java, there's actually a number limitation of what Java can handle with a certain data type. So in that case, it's 2,147,483,647. So if you were to calculate a number beyond that, it would actually not give you the right answer. But as long as a programmer knows these limitations, it's really not a problem. And any good programmer would know these things, but it's easy to miss, and you'll see that when we talk about a couple of examples. So we're now going to take a look at a real-life event that was in part caused by a programming limitation that was not discovered before the code was actually used in production. So June 4th, and by the way, if you want to see the video, here it is. Actually, let's hop out and have a look at it and see if we can't. I think it's we'll just watch the first little bit here.
By the early hours of the morning of the 4th of June, Ariane 5 stood proudly on ELA 3, waiting for the final countdown. No one would sleep much that night. They never did before any launch. The skies opened again, and the tropical rain poured down over the rocket. There were doubts if it would be able to launch the next day. Its prospects looked poor. By the next morning, the forecast had improved slightly. A final decision to go was taken.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, feu. Allumage. Décollage. propulsifs sont normaux et la trajectoire est normale.
Okay, so June 4th, 1996, 37 seconds into this launch, the onboard computers decided the rocket was 90 degrees off course. They made an automatic adjustment to the trajectory as the rocket was traveling at the speed of sound. There are many theories as to what caused this explosion. In fact, MIT wrote an article that discusses and describes the 501 failure, and it's actually a pretty interesting article if you're interested. So this article lists some of the technical events that occurred, and one that I want to point out to you is that the internal SRI software exception was caused during execution of a data conversion from a 64-bit floating point to a 16-bit signed integer value. So what does this all mean? It is one of the many programming limitations that occur in different programming languages. What the software was trying to do was to store a value that's one type into a variable that was not designed for it. And more specifically, the floating point integer had a value greater than what could be represented by a 16-bit signed integer. This resulted in an operand error. The data conversion instructions in Ada code were not protected from causing this operand error. So the point here is that some programming languages have built-in mechanisms to detect such possible errors, but Ada is not one of them, at least as of that time. So this is a real-life example of how programming limitations can cause serious problems. It is worth noting that there were several things that went wrong and that it was not just this software error, but nonetheless, this software error did have an impact on this event. So now that we have seen an example and talked about some of the programming languages and their limitations and the problems that they can cause, in particular this real-life event, the Ariane 5 Flight 501 explosion. So what I would like for you to do is to contemplate these questions for our online session. Suppose we knew the identity of the people who made the decision to omit the code necessary to handle the arithmetic overflow error, which caused the rockets during the Ariane 5 flight to self-destruct. Would you hold these people responsible for that accident? Suppose lives had been lost due to the Ariane 5 disaster. Should anyone be considered guilty of a criminal negligence? So be prepared to discuss this in our online session. So let's take a look at another case called the Pentium floating point divide. Basically, what happened here was that this chip was not calculating division problems correctly. When faced with a division question, some answers returned were not correct. If you haven't done so already, you should read about this case, and as a reminder, this case is discussed in your textbook. I want to point out that this is not specifically a software or hardware error. Your book makes a case for this being a firmware error, which we haven't really talked about yet. So firmware is a set of instructions that are essentially embedded in a piece of hardware. So in this case, it wasn't the hardware that failed, it was the firmware. So all of our hardware devices like phones, cameras, printers, etc., all have firmware that control the device. Today, many devices let us upgrade the firmware by downloading an update and installing that update right to the device. But back in 1994, there was no way to fix this problem with actually replacing the hardware, without actually replacing the hardware, and that was could be expensive. So how bad was the error? This is just an example, and you can find this sample example on Wikipedia. But in this particular division, 4,195,835 divided by 3,145,727, it resulted in 1.33373 and so on, when the answer actually should have been 1.3338 and so on. So you can see here that this issue is occurring at about the fourth place after the decimal point. where we should be getting 1.338 instead of 1.3337. So it's not unusual to get answers that may vary by 10 or 15 places after a decimal point, but this is a much larger error than we would typically see in calculations. So Intel said, which is the maker of the Pentium chip, that they would replace hardware for users who could demonstrate a need for that precision. So a question for you to consider and to be ready to discuss here is, did Intel have a moral obligation to replace the defective Pentium 5 chips, even for those users who had no need for high precision? I'd like for you to think about that and contemplate it. There's some other questions. Let me see here. Feels like hang on for a second. I apologize. Here's some other questions. Yes. So, man. Okay, so we have this question. And then there are other questions here I'd like you also to focus on. So when employees of Intel first discovered the bug, did they have an ethical responsibility to make the problem public? I'd like for you to contemplate that and support your stance. And then also, suppose a bank was relying on computers that had the Intel 5 Pentium chip to perform extensive computations relating to investments. Suppose further that the error in the chip caused the bank to lose a significant amount of money. Does Intel have a moral obligation to compensate the bank for its loss? And by the way, this is not a question of Intel's legal liability. It's more about a moral question that I'd like for you to contemplate in our online sessions. Okay, so software complexity. So we've looked at how software is limited in terms of its ability to store different types of numbers, but there's also a problem when we're developing software and that software can get very complex. When a computer program has some kind of decision point, and that could be an if statement or a for loop or a while loop or any decision point, as soon as you put these decision statements into a program, then the program becomes a little more complex. And as a program becomes more complex, it becomes more and more important to test a program and make sure that it's going to work at all of these different decision points. So we have seen that software can get very complex. Even a very short program can be prone to errors if we don't do enough testing. But then larger pieces of software, such as Photoshop, and other software like that, is used to operate cars. We have software that operates cars, and the code can get into the million lines of code. So it's just a sign of how difficult it can. So this focuses us to think about what should software developers do in order to ensure that their software is reliable and trustworthy. So let's take a look at cars and their software. Cars now have software that will allow them to self-park. And these links here are all links that talk about that. So the first video here demonstrates the self-parking feature. There are many like this. I just grabbed this one as an example. So take a minute to watch this so that you can get an appreciation for how this works. The second article talks about what happens if your self-driving car crashes. Who is responsible for that? Who do you think? Should it be you? Should it be the manufacturer? Should it be the software developer? And then there's a very recent story that happened in July of 2015 where 1.4 million cars were recalled because hackers were able to take control of the brakes and other systems. This may remind you a little bit about Chris Roberts, who allegedly hacked into the airplane entertainment system to take control over the airplane and actually cause it to climb. So take time to watch these videos and read these articles, and then some questions for you to consider come in this following slide. So if you're using a car that has self-parking feature and the car collides with the parked car, are the software developers morally responsible? Are you morally responsible? Could this problem have been avoided with additional software testing? Why or why not? So I would really like for you to consider these questions, and we'll talk about them in our online session. So you can see when you put decision points into a program, it can make the complexity of that program grow very quickly. If you're going to test a program with decision points, each decision point increases the number of test cases that we would have to consider. Even a very simple yes or no survey can be complex. So suppose a hospital has a 10 yes or no question survey and a piece of software that makes diagnosing or gives some kind of information back in response to these 10 questions. Just with 10 yes or no decision points, there are now 1,024 different combinations of yeses and nos to be tested for. If there were 20 yes or no questions, we would be up to over 1 million possible test cases to consider. So you can see how a program, even a fairly simple program like this example, which would be like 50 lines of code, still can be very complex when it comes to having to test all of these different examples. So let me go back here. So the question is, how do we deal with this kind of complexity? And the answer is not just testing. The answer is more complex than that, and it involves looking at actual process of software development. So before we look at that process, there's another case that you should familiarize yourself with. This is not in the textbook. It happened more recently than when the textbook was published. I would like for you to read some of the news articles about the healthcare.gov website. You may or may not be familiar with this, but the site opened in 2014 and encountered problems on the very first day. They were actually pretty significant problems. And I would like for you to kind of analyze what you find as you're looking up articles on this and figure out what were the causes of this problem and did anybody actually accept the blame. There is a video here that you can watch about it, but you may want to do more research and find additional videos and articles that give you the background of the issues with this website on day one. Now, we've talked about this one in a previous chapter, but I'll mention it again. This was the TheraAct 25. I believe we discussed it back when we were in chapter 2. But the long and short of this one was a radiation machine that was used to help cancer patients had a software issue, and it actually was administering higher doses of radiation than what it was supposed to, and people were getting burned, and in some cases people actually died. These are just pictures. It's pretty horrific, actually. So there are a lot of questions to ask regarding who or what was responsible for this issue that led to the TheraAct 25 machine failing. Certainly a lot of human factors contributed to this issue. At first, when problems were occurring, people didn't believe that it could be possible, that it could possibly be the result of a machine, and it took a while for them to unravel this and determine this. You would think after one bad case they would have shut the machines down, but the truth is people didn't know after those 1 or 2 cases what was going on. So Douglas Birch is an ethicist who had criteria for judging whether a person should bear moral responsibility for an action. And so the questions for us to consider here are, was the software developer for the THER Act 25, should he be considered morally responsible for what happened in these cases? There was also a quality assurance engineer who worked on this program. Should he bear any moral responsibility? So Douglas Birch came up with the 3 ideas for determining whether a person should be considered morally responsible for an action a person was involved in. So read these 3 items by Birch and determine based on these criteria whether the software developer or the quality assurance engineer should have been morally responsible for this incident. And we will discuss that in our online session. So we have seen 3 cases here: the THER Act 25 machine, the healthcare.gov, and the idea of the complexity of car software. Software that is too complex becomes impossible to test completely. Certainly some testing should be done, but we won't be able to test all possibilities. Remember, if there's the case on the 10 questions and how many testing cases that would cause. So what's the solution? Some people would argue that software should not ever be used in safety critical situations. Do you agree? I'd like you to contemplate that, and possibly we'll bring that up in our online discussion. So when software can't be tested, there are some things we can do. So when software can't be tested, what can we do to help ensure that we can feel safe about using complex software that can't possibly be tested for every possible bug? One way is to look for ways to improve the software development process. So besides testing software for bugs, improve the process so that the bugs don't happen in the first place. And just for a point of discussion, bugs will always exist because humans are involved, but the point here is to minimize them. So we do that by looking at the software development lifecycle, which is gathering requirements, the specification and design, and then, of course, the implementation. The notion being that if we do these steps carefully, we can avoid the bugs that might have occurred otherwise. So what have we seen so far? So we have we see that computer failures happen because humans make mistakes. Those mistakes can be with making or using hardware, or the software that is developed, or working together with a client and a developer. Those are the 3 primary reasons that computers fail. But now we want to take a look at software that is designed maliciously. That is, sometimes computer failures happen because humans have immoral or unethical intentions. So you're familiar with these things. We're talking about spyware and adware and viruses and the like. I want to give you an example of one such malicious type of software, and this is a phishing email. Phishing refers to tricking users into or luring users into divulging some kind of private information. And there's actually a real-life case that happened here several years ago at Miami, and it was a phishing email that went out that looked very authentic, meaning it looked like it came from our own Miami's payroll department, and it asked people to verify their banking information for their direct deposit of their paychecks. So as it turned out, it was not from Miami at all, and it was a phishing attempt to get people's banking account information. And unfortunately, in this case, and I'm sorry to say, several employees here fell victim to this attempt and gave their credentials out. Fortunately, our security department here in IT found that this issue pretty quickly and was able to take measures to kind of shut it down and mitigate any further victims falling prey to this attack. But if you're not overly aware of phishing attempts and emails, I encourage you strongly to do so. because they're becoming more and more sophisticated, and as a general rule, if there's anything that's asking you for information that you find that would be confidential, really think twice before you click on any of the links. Okay, so malware. So these are all examples of malware, and malware is just short for malicious software. And there's a variety of different types of malware, and we're not going to go into details of all of these, but you should be at least familiar with these we have listed here. So a worm. A worm is a program that makes copies of itself and propagates those copies through a network to infect other computers. A virus, which is similar to a worm, but it resides in another program that must be executed in order for the virus to propagate. And then, of course, the ever-famous adware. And if any of you have ever experienced adware taking over your machine, it's just a nightmare. So it's a program meant to deliver unwanted advertisements to your computers. And oftentimes, at least a couple years ago, it would render your computer unusable. Spyware, which is a program that is secretly installed for the purpose of collecting information about the computer's users. Trojan horse, which is a software that masquerades as an innocent or useful program, but that is actually designed for a malicious purpose. And then rootkit. We've talked about this several times already. It's a program that embeds itself into a computer's operating system, and it acquires special administrative privileges that would normally be only available to administrative users or the operating system itself. So there's a story that you should familiarize yourself with from SourceForge. SourceForge.net is a place where software developers could distribute their open source software projects. And recently, SourceForge began wrapping their downloads with an extra installer that they put adware on computers. So take a look at this article about the story so that you're familiar with this case. Hackers. So we use this phrase hackers. Hackers are often people who write and deploy malware. There was a time that being a hacker was a good thing because it meant that you were good at using a computer and solving problems by programming. Today, mostly hackers are not viewed in such a positive light. Although there are still terms for good hackers and bad hackers, but that's not what we're talking about here. So you may have heard of hackathons, and if you haven't, you should look up hackathons and answer these questions. Find information about hackathons. What are these events, and which definition of hackers is being used? I'd like to discuss that in our online session. So ethical hacking. Can hacking be considered ethical? So for example, Chris Roberts, who again allegedly hacked into the airplane system to demonstrate that it is possible to hack into an airplane system. One of his premises, I believe, was he was trying to show how easy it was to do, and that if he could do it, it was really susceptible to other unethical people doing it. So now that I just gave you that, it kind of begs the question, is that ethical what he did? And if so, what definition of ethical are you using? So I'd like for you to watch this video and then answer this question. What is Karen's argument in favor of hackers? And what theory of morality seems to best support her argument? Be prepared to discuss this in our online discussion. So finally, one more case to familiarize yourself with that will further complicate the question of can hacking be considered ethical is the Stuxnet worm. This is another TED Talk video given by Ralph Langer, and there's a lot of technical details as to what the Stuxnet worm was, but kind of learn the background of Stuxnet and then watch the video and see if you can answer the question. Who is it that Ralph Langer argues is the leading force behind Stuxnet? And would you consider the people who developed Stuxnet to be ethical hackers? Okay. And this is just a list of references used throughout this presentation. We talked about a lot of them, so I just included them here. So that kind of completes Chapter 5. And like other online sessions, we will discuss the questions that I have posed here in our online session. And I look forward to that. Thank you.